We're always talking about how things change, right? The speed of a car, the stock market. But what if we could actually measure how the change itself is changing? Well, that's exactly what we're diving into today with higher order derivatives.
So let's start with this big question. We know a derivative gives us the rate of change, like a slope on a graph or the velocity of an object. But that rate is almost never constant, is it? It speeds up, it slows down, it reverses. So how on earth do we measure that?
It sounds kind of like a brain teaser, doesn't it? A derivative of a derivative. But the logic here is actually super simple. Think about it. When you find the derivative of a function, you just get another function. So what's stopping us from taking the derivative of that new function? Absolutely nothing. And that's the core idea.
And this whole process of, stacking derivatives on top of each other has a name. It's called a higher order derivative. So the second derivative is just the derivative of the first one. And the third derivative, you guessed it, it's the derivative of the second. Each one gives us a brand new layer of information about how our original function is behaving.
Okay, so what do all these different layers actually mean? This is where it all starts to click and honestly where it gets really, really cool. You can think of each derivative as a new lens that lets us see the same function or the same moving object in a totally different way.
Now look at this table. What's so amazing here is how it connects two completely different worlds. On the geometry side, the first derivative is the slope, but in physics, that's velocity. Then you go down a level. The second derivative tells us about the graph's concavity. Is it curving up or down? In physics, that's acceleration. And then we get to the third derivative, which describes the change in acceleration. It's actually called jerk. And yeah, that brings us to my favorite part. The third derivative has, without a doubt, the best name in all of calculus, jerk. Seriously, it represents how suddenly the acceleration is changing. You know that jolt you feel when an elevator suddenly starts moving? That feeling is jerk. We can actually describe it with math.
All right, so that's the theory, but how does this actually work when you're doing the calculations? Let's get our hands dirty and walk through a really straightforward example, step by step, to see this thing in action. Okay, so here's our starting point. We've got a pretty basic polynomial function. Our goal here is to find its second derivative, which means, of course, the first thing we have to do is find the first derivative.
So we just need to apply the power rule. For that first term, x to the fifth, the 5 comes down in front and the exponent drops to 4. Boom, 5x to the fourth. For the second term, 3 times the 2 in front gives us 6 and the exponent drops to 2. So we get 6x squared. This new function, y prime, gives us the slope of our original curve at any point.
And now for the final move. We just do the exact same thing, but this time to our first derivative. Applying that power rule again, 4 times 5 is 20, so we have 20x cubed, and 2 times 6 is 12, so we have 12x. And there you have it. That's our second derivative. This new function tells us all about the concavity, the curvature of our original graph. Okay, so we can crunch the numbers, but what's the point? Why does this matter? Well, let's bring this out of the abstract and see how it gives us incredible detail in a real-world scenario. Let's pretend we're tracking a drone.
Here's the setup. We have this function s of t, and it tells us the drone's height at any given time, t. So our mission, should we choose to accept it, is to figure out exactly what the drone is doing. Not just where it is, but how fast it's going and how that speed is changing at the exact 3-second mark.
First things first, need the velocity. And remember our chart? Velocity is just the first derivative of the position function. So we take the derivative of s of t, and that gives us this brand new function, v of t. This tells us the drone's velocity at any time we want. Next up, acceleration. How do we find that? Well, we just differentiate our velocity function. The derivative of v of t gives us our acceleration function a of t. And of course, this is also the second derivative of the position function we started with. Okay, so we have our tools now. We've got the velocity function and the acceleration function. Now for the fun part. Let's plug in our time, t equals 3, and get a snapshot of what this drone is doing at that precise instant. All right, when we plug 3 into our velocity function, we get 1 meter per second. So what does that mean? Well, since the number is positive, we know the drone is moving up. But since it's a pretty small number, just 1, it's not going up very fast. It's rising, but kind of gently. Now for acceleration. We plug 3 into the acceleration function and get 6 meters per second squared. This is what's so powerful. Because the acceleration is positive, it tells us that the drone's upward velocity is increasing.
It's actively firing its motors to push itself upwards even faster. So, let's zoom out for a second and put this all together. What is the one big idea you should walk away with?
Really, it's this. Higher order derivatives let us peel back the layers of how things change. We start with position, then we peel back a layer to get velocity, then we peel back another to get acceleration. Each layer gives us a richer, more detailed, more dynamic picture of what's really going on. And that leaves us with one final thought to chew on. We know the third derivative is called jerk. So what do you think that tells us about something like a roller coaster? The next time you're on a ride and you feel that sudden lurch that throws you back in your seat, or you're in a super smooth high-tech elevator, you are physically feeling the third derivative. It's the mathematics of smoothness and shock. Pretty cool, right?